Welcome to Theory of Computation. This is lecture number 23. In the last lecture, we started looking at two classes of problems. The first class we called was P, polynomial time. Polynomial time, or P, the class P, contains all those languages or all those problems that we can solve in reasonable amount of time, in practical time. Actually, in polynomial time. That's the exact definition of P. So that's simple enough to understand. If you have a problem and you find an algorithm for that problem that can solve the problem in polynomial time, then you would say that this problem belongs to the class P. Let us think about a few examples of things that we know are in P. Since you have taken an algorithms course, you know of many problems which belong to the class P. Actually, in an algorithms course, you just don't prove that problems are in P, you also try to reduce the running time. So, for example, you have studied depth first search and breadth first search, and that shows that given a graph, the problem of telling whether a vertex S is connected to T is in P, since we have a polynomial time algorithm for it. In fact, DFS and BFS, you can prove they run in linear time, and therefore actually we have a linear time algorithm. However, note that we have a linear time algorithm. In order to convert that linear time algorithm to a single tape Turing machine, that requires some overhead. When we are talking about models of computations, what we want to do is we want to say that the definition of our class that we are talking about is independent of the model of computation. So in this sense, P is an extremely robust class. You can think of P to be the set of all problems that can be solved by, say, Java programs in polynomial time, C++ programs in polynomial time, K-tape or 5-tape Turing machines in polynomial time, or 1-tape Turing machines in polynomial time. All these definitions are equivalent. So the class P is the set of all problems that can be solved in polynomial time. Here there is a subtle point, and you must understand this subtle point very carefully. When we say that the algorithm or the Turing machine takes polynomial time, we mean that the time is polynomial in the length of the input. A major confusion arises when you start looking at numbers. So suppose that you have a number n. In this case, I can express the number n in binary, and expressing a number n in binary requires very little space. It requires log n space at most. If you take a number n and you look at the binary representation of it, you would easily see that the binary representation requires only log n bits. Therefore, when you're dealing with numbers and you are going to come up with a polynomial time algorithm, remember that if the input is n, then the time should be polynomial in the length of n, which is log of n. The best way to think about it is, if you take an algorithm which is dealing with numbers, when it takes k-bit numbers, then the time should be polynomial in k, not in the number itself. As an example, we saw how to compute the GCD using the Euclidean algorithm. The first algorithm we looked at was not a polynomial algorithm. That algorithm was just trial division. If you give me two numbers, x and y, I can try to find the GCD by dividing x and y by dividing x and y with each number 1, 2, 3 up to minimum of x and y. This algorithm actually does, so let's say x is the smallest number, then this does at most x divisions. This is not polynomial in the length of x. This is exponential in the length of x. Then we saw Euclid's algorithm, which takes polynomial time in the length of the input. The beauty of Euclid's algorithm is that if you give it two k-bit numbers and ask it to find the GCD, it performs at most 2k divisions. And therefore, that's a polynomial time algorithm, since we know how to divide in polynomial time also. The second class that we want to look at is called the class NP. The class NP is the set of all problems that can be that can be solved in polynomial time by non-deterministic Turing machines. What we need to do is understand this class more thoroughly. The reason that P is so intuitive, that you understand the definition of the class P so easily, is because you've seen lots and lots of examples of problems which are in the class P. Whereas non-determinism in Turing machines or non-determinism in algorithms is a new concept for you. One way to understand non-determinism was to say that the machine is allowed to guess. We looked at a non-deterministic Turing machine that makes a guess. What it does is it writes n ones on the tape, and then it scans the input and it has two choices, either to change the 1 to a 0 or leave it alone. When it has scanned the input again, if you look at the branching of this Turing machine, each branch has guessed a different number. So that is the power of non-determinism. The machine is allowed to make guesses, and therefore what you want to do is now you want to design non-deterministic Turing machines. Let's continue our lecture today. Today we will once again look at the class NP. We would review a bit of what we had done earlier. Then we would try to look at many examples of problems which are in NP in order to get a feel for what NP is. After doing that, we will look at another formulation of the class NP in terms of verifiers. This is going to be a different way of looking at the class NP. So we will have two ways of looking at the class NP. One is through non-deterministic Turing machines, the other is through verifiers. Then we will prove that both these definitions, the non-deterministic definition that comes from the non-deterministic Turing machine side and the verifier side, give us the same class NP. After that, we would talk about what is the relationship between the class P and NP. Let's start with today's lecture. We looked at this very simple non-deterministic Turing machine. This is the most important Turing machine as far as non-determinism goes. If you understand that, you will be able to understand the concept of non-determinism. This Turing machine, if it is in state Q0 and it sees a 1, what it does is it either changes the 1 to a 0 or leaves it alone and moves to the right. When it sees a blank, it just accepts the input or its computation finishes. We call this Turing machine the guessing Turing machine. If we run this Turing machine on a sequence of n ones, then if you look at the computation of the Turing machine, it has 2 to the n branches, and each branch corresponds to a string of zeros and ones of length n. So we have this guessing Turing machine, and this Turing machine on each branch can make a guess of all the 2 to the n possible Turing machines. We will use this Turing machine to show that problems are in NP. Let us look at an example of a problem in NP now. We define composites to be the set of all integers n such that n can be written as p times q for some integers p and q greater than 1. So the definition of composite numbers is the good old definition that was told to you in your elementary school. Well, how will we design a non-deterministic Turing machine to accept composites in polynomial time? Well, the basic idea is if the machine gets an input n, it will guess the first factor p. So it will guess, suppose if it gets a k-bit number, then it'll guess a k-bit number p, and then it'll guess q. Then it will check if p is greater than 1 and q is greater than 1, and if p times q equals n. So that is our non-deterministic Turing machine, and that accepts composites in non-deterministic polynomial time. If you look at this non-deterministic Turing machine, you realize that every composite will be accepted by some branch, namely the branch that guesses p and q correctly. So suppose the input to this number was, to this machine was 20, then the branch that guesses p equals 5 and q equals 4 will accept. The branch that guesses p equals 2 and q equals 10 will also accept. So if the number is composite, there is at least one solution to this equation n equals p times q with p greater than 1 and q greater than 1. So the branch that makes the correct guess will accept. On the other hand, every prime will be rejected by all branches. The reason is, by definition, a prime number cannot be written as a product of two numbers, both of which are not 1. So, since we have a check in the end, which checks if p is greater than 1 and q is greater than 1 and p times q is equal to n, this check will never come out to be true, and so all branches of the machine will reject a prime number. Therefore, this is a non-deterministic Turing machine that solves composite in non-deterministic polynomial time. Let's now look at another example of a problem in NP. Let us define ham path to be the encoding of a graph G along with two vertices S and T. And the question here is to tell whether there is a Hamiltonian path from S to T. So you will be given a graph G and two vertices, two special vertices S and T in it, and the algorithm has to output yes or accept the input if and only if there is a Hamiltonian path from S to T. This is the problem. This is called the Hamiltonian path problem, and in this case we are assuming that the graph G is a directed graph. So the question is, given a graph and two vertices, can you tell in non-deterministic polynomial time if there is a Hamiltonian path from S to T? Let's recall what a Hamiltonian path is. Since if we are going to try to understand this problem, we should recall the previous definition. Remember that a Hamiltonian path is a path in a graph that contains every vertex exactly once. So a path that starts from S, goes through all the vertices of the graph, and eventually ends at T and never repeats a vertex is called a Hamiltonian path from S to T. Let us look at an example. Here is a graph which has a Hamiltonian path from S to T. As you can see, what I have done is made the path from S to T with bold arrows in order to emphasize the Hamiltonian path from S to T. So this is a graph which has a Hamiltonian path from S to T. So if this were the input, the algorithm would be required to say yes, or it will be required to accept this particular graph along with the node S and T. Let's look at another example. If you look at this example, this graph does not have a Hamiltonian path from S to T. In this case, it is not very easy for me to show you that this graph does not have a Hamiltonian path from S to T. Therefore, what you should do is you should look at this picture and convince yourself, of course after the class, that it does not have a Hamiltonian path from S to T. So, if I give you a graph in general, your algorithm or non-deterministic Turing machine is supposed to analyze this graph and tell whether there is a Hamiltonian path from the vertex S to the vertex T. S is called the source or the start vertex, and T is called the terminal vertex. So in this case, you're given a graph, a source and a terminal vertex, and the question is if there is a Hamiltonian path from S to T. Let's now look at a non-deterministic Turing machine that accepts this problem in polynomial time. Let's first think about how we will make such a non-deterministic Turing machine. Well, remember the power of non-determinism. Non-deterministic Turing machines have the power of guessing. So if you give me a graph and ask me if there is a Hamiltonian path from S to T, I can either try to find that path, but since you have just asked me to come up with a non-deterministic algorithm, what I can do is just simply guess that path and then check whether it is a Hamiltonian path from S to T. So let's look at this Turing machine formally. Here is the Turing machine that accepts Hamiltonian path. It's a non-deterministic Turing machine. First, it gets an input, which is a graph G and a special vertex S and T. What it does is it computes the number of vertices in G, let's call it n. Now it uses the guessing Turing machine to guess n vertices v1 up to vn. And these are the n vertices that it has guessed. So it runs the guessing machine n times to guess n vertices. Without loss of generality, we can assume that the vertices in the graph are actually labeled by numbers from 1 to n. So it guesses n vertices. Then it has these n vertices. First, it checks whether all these vertices are distinct. Then it checks if v1 happens to be the source vertex. Then it checks if vn is the terminal vertex. And finally, it checks if vi and vi plus 1 is an edge in the graph for each I going from 1 to n minus 1. So this Turing machine simply guesses a path of length n in the graph. Then it verifies that each vertex in there is distinct, because a path is not allowed to have loops in it, so no vertex is supposed to recur. So it checks if all the vertices are distinct. Then it checks if the first vertex is the source, and then it checks if the last vertex is a terminal vertex. And finally, it checks whether this alleged path is actually a path in the graph. If there is an edge from S to V2, V2 to V3, V3 to V4, and so on all the way up to T. If all these checks are verified, then the machine has actually found a Hamiltonian path and it can accept. Now let's think about what would happen if I were to give this algorithm a graph G which had a Hamiltonian path from S to T. Well, as I'm using a guessing machine, a lot of the branches are going to be wrong guesses. So they are all going to reject. However, there is at least one branch which will make all the right guesses of the vertices which are along this path. And that particular branch will accept, because it will be able to verify that this path is a path from S to T. So if the graph is Hamiltonian, at least one branch will accept. On the other hand, if the graph does not have a Hamiltonian path from S to T, then no branch of this Turing machine, no branch when you run this Turing machine, no branch will accept, because it doesn't have a Hamiltonian path. Therefore, it is not possible for it to be able to successfully check all the checks that it's making, because by definition, all those checks prove that the graph have a Hamiltonian path. So we have a non-deterministic Turing machine that accepts the Hamiltonian path problem. If you look at the time complexity of this algorithm, see how much time it takes, it's not difficult to convince yourself that this takes polynomial time. Now, what we have is a Turing machine which, if you give it a graph G which has a Hamiltonian path from S to T, at least one branch will accept. And if you give it a graph which does not have a Hamiltonian path from S to T, no branch will accept. Thus, this non-deterministic Turing machine accepts Ham path. It's also easy to see that the length of each branch is polynomial in n, the number of vertices in the graph. Thus, this is a non-deterministic polynomial time algorithm that accepts Ham path. Non-determinism is quite an elusive concept for many students. Once you have an elusive concept and you want to understand it, the best way to go about it is to, first of all, study it a lot. That hard work is one thing which is always going to help you. But the other thing you can do is try to understand that concept in different ways by looking at that concept from different points of views. Well, non-determinism, we can think about it as formally the definition of non-deterministic Turing machines. The second way we looked at it was, we said, well, these are algorithms which have the power of guessing. Now we will look at another way of looking at non-determinism through verification algorithms. Verification algorithms are going to be deterministic algorithms, algorithms that we are already familiar with. If you look at our previous two examples, what was really happening? We looked at composites and we said that it was in the class NP. We have a non-deterministic polynomial time algorithm for it, and then we looked at Hamiltonian path. What both these machines were doing were in some sense guessing something and then verifying. So for example, the first Turing machine, when it got a number n, it wanted to prove to itself that the number n is composite, so it guessed two numbers p and q, and then verified that p times q equals n, and thereby proving to itself that the number was composite. Similarly, the second Turing machine that we looked at, which actually was trying to see if a graph has a Hamiltonian path, what did it do? It essentially guessed the Hamiltonian path and then verified or proved to itself that there is indeed a Hamiltonian path in the graph. So this concept could be well understood if we look at a new thing called verifiers. So let us say we have a language A. A verifier for the language A is going to be an algorithm or a Turing machine. Remember that an algorithm is the same thing as a Turing machine. So this algorithm, we are going to call it V. It's called a verification algorithm, such that A is the set of all W such that V accepts W comma C for some string C. So this is a formal definition. What you do is A is the set of all W such that for them you can find some C, and when you give W comma C as an input, V will accept that input. Intuitively, it doesn't seem to make sense what this concept is saying, but if we give each part of this definition some meaning, then it would be clear what we are talking about. In this case, V is going to be called a verifier, and it takes two inputs, W and C. C is called the certificate or a proof. It accepts a W comma C if C is a correct certificate of the fact that W is in A. So think of the verifier as a person who does not actually solve the problem but checks correct solutions. So for example, if you look at your grader, the person who is grading your exam, then their job is not to solve the problems or find proofs, but just to verify that your submitted proofs are correct or not. Now, if the grader is a perfect grader, then suppose if I give you a problem, the grader will accept all those solutions which are correct. In that case, he'll give them, let's say, 10 out of 10, and he or she will reject all the solutions that are incorrect. So that is the basic idea of a verifier. Verifier is an algorithm that only accepts or correct proofs or correct certificates. Let's elaborate on this point a bit more. For example, let's think about composites. Suppose that I want to convince somebody that a particular number is composite. How would I go about doing it? Well, if I somehow manage to factor the number, which may take me a long time, I may use a supercomputer or some other method, ingenious method, or I may just stumble upon a factorization of the number by chance or luck. But once I have factored the number, then the two factors are a proof that the number is composite. And furthermore, this proof is easily verifiable. I can give that proof to anybody in high school, and what they will do, I'll say, look, this number is composite. The reason is because I have been able to find P and Q, and if you multiply P and Q, you get the number N back. And they will be able to easily verify this proof. So a verification algorithm takes W as an input and some certificate which proves that this W is in the language A. If you give this verifier some W and a wrong proof, wrong certificate, it would reject that this is a wrong certificate. So for example, if I were to try to prove that 15 is composite by saying that 15 is 3 times 8, then 3 times 8 is not a correct certificate that 15 is composite. On the other hand, if I give the certificate 3, 5, then 3 and 5, if you multiply them, you get 15. So 3 and 5 show that the number 15 is composite. So a verification algorithm only checks if a proof is correct. So verification algorithm takes two inputs, W, C. The first part is what we're trying to prove is in the language. The second part is a proof of the fact that W is in C. And then it accepts only correct proofs of the fact that W is in A. Now, the way we will measure the running time of a verification algorithm, it is going to be measured in terms of W, the input, which we are trying to check whether it is in A or not. In this case, the length of the proof will be ignored. So we will say that V is a polynomial time verifier if it runs in time which is polynomial in the length of W. If A has a polynomial time verifier, then we'll say that A is a polynomial time verifiable language. So, which languages are polynomial time verifiable? Well, our claim, which we will prove later today, is going to be that exactly the languages which are in NP. But let's continue with some examples. So, is it true that the language composites is polynomial time verifiable? So, can you make a program which will accept correct solutions or correct proofs of the fact that a given number is composite, and it only accepts correct proofs and reject all other proofs? Well, first of all, we have to think of what would be a proof that a number is composite. Well, the very definition of compositeness tells us what would be a nice proof that a number is composite. All we have to do is give two numbers which we, when multiply, give us the original number back. That will show that the number is composite. So here is a verification algorithm, a polynomial time verification algorithm for composites. The verifier takes as input n and a pair p, q. First it checks if p and q are both smaller than n. If not, reject. So this way the verifier will not take a long time reading the proof, because it will just stop reading if the proof is too long. The second thing it will do is it will multiply p and q and see if that is equal to n, and it will also check if p and q are greater than 1. If all these things are true, it will accept, otherwise it will reject. So this is a polynomial time verifier for composites. It's very easy to make. It takes the obvious solution or the obvious proof which of the compositeness of n and checks it in polynomial time. Essentially all it does is performs a single multiplication and a comparison, and therefore this algorithm runs in polynomial time, and it verifies whether a number n and the proof that a number n is composite is correct or not. Let's look at another problem which is polynomial time verifiable. Let's now try to prove that Hamiltonian path is polynomial time verifiable. Well, what we have to do is first think of what would be a correct proof that a graph has a Hamiltonian path from S to T. The best way for you to think about it is, suppose you have a graph which has a Hamiltonian path from S to T, and you want to convince someone that this graph has a Hamiltonian path from S to T. What would be the easiest way for you to convince your friend that this has a Hamiltonian path from S to T? Remember when we were trying to understand the definition or recall the definition of what a Hamiltonian path was, I showed you a graph. And I said that this graph has a Hamiltonian path from the vertex label S to the vertex label T. How did I convince you of that? If you noticed, what I did was I took the path from S to T, the Hamiltonian path from S to T, and highlighted it. So, if you want to convince somebody that a graph has a Hamiltonian path from S to T, the best way to do that, the best way to prove it to them, or the best way to convince them is to highlight that path. Or, in other words, just tell them what the path is. So, you tell them what the path is from S to T, which is the Hamiltonian path. Well, how would we check this? your claim. So you give them a graph and say, there's a Hamiltonian path from S to T and here is the path. How would they check that your claim is correct? Well, all they have to do is to check whether your path is a Hamiltonian path in the graph. And for that, they'll have to check whether the first vertex is S, the last vertex is T, and whether on your path all the vertices in the graph appear, and whether from each vertex in your path to the next vertex there is always an edge in the graph. This is the simple check they would do. And this is a verifier which will verify that a graph has a Hamiltonian path from S to T, but it has to be given the proof or the certificate or the Hamiltonian path. It is itself incapable of finding it. So let's look at this verifier a bit more formally. Here is the verifier for it. On input, which will be first a graph and two distinguished nodes S and T, and a list of n vertices, it will check if the first vertex is S and the last vertex is T. It will check if all the vertices are distinct. If they're all distinct and the graph has n vertices, then this path is going through all the vertices of the graph. And eventually it will check if Vi and Vi plus 1 is the edge for all I going from 1 up to n. Now note that if there is a Hamiltonian path from S to T, then we can give that path or those n vertices to this verifier and it will accept that. If someone has found such a path, it is very easy to indeed verify that it is a Hamiltonian path. On the other hand, if the graph does not have a Hamiltonian path, then you can try to give it any path, any other path, and this verifier will reject all of those proofs or all of those certificates, because since these are not Hamiltonian paths, either they'll not start from S, or they'll not end at T, or they'll repeat vertices, or there'll be some vertices missing, and it will be able to detect that very easily. Now we will define the class NP. NP, the class NP, we are going to define it in two different ways. Firstly, NP is the class of problems or class of languages that have polynomial time verifiers. So NP is the set of all those problems which have polynomial time verifiers. Another definition of NP is that NP is the class of languages that are decided by polynomial time non-deterministic Turing machines. So we have two definitions of one class of problems that we want to define. Well, actually, I shouldn't be saying we have two definitions of one class. What we will do is we'll prove that these two definitions are equivalent and they identify or they classify the same problems. Thus, if you take the first definition or the second definition, you get the same class of problems. The way you should think about NP is these are easily verifiable problems once some certificate has been found. So these are problems where the membership in the language has some easily verifiable certificates. P is the set of problems that we can actually solve easily or practically or in polynomial time. NP is the class of problems that we can verify in polynomial time. Now, let us be careful and let's define NP sub 1 to be the class of languages that have polynomial time verifiers. Let us define NP sub 2 to be the class of languages that are decided by polynomial time non-deterministic Turing machine. What we want to show is that NP sub 1 is equal to NP sub 2, that both these definitions are equivalent. If we do that, then we'll be justified in calling both of these classes and giving them the same name, which we'll call them NP. So let us take a language L, which is in NP sub 1, and we will show that it is also in NP sub 2. Let L be a language in NP sub 1 and V be a verifier for this language. The verifier runs in polynomial time, so let's say that the running time of this verifier is d times n to the k, where n is the length of the input or the first component of the input. So we take this verifier, which is a verifier for a language L and runs in polynomial time. What we want to do is now show that this same language L is accepted by some non-deterministic Turing machine in polynomial time, in non-deterministic polynomial time. How will our non-deterministic Turing machine look like? Think about it. We do not know much about this language L. We just know that it has a polynomial time verifier. So our non-deterministic Turing machine will somehow use this polynomial time verifier. Well, what we can do is we can try to run this verifier on different certificates. But which certificate? We'll have to find the right one, and only then it will accept. The idea is non-determinism has the power of guessing. So what we can do is we can simply guess the certificate and run this verifier. So our non-deterministic Turing machine looks like as follows, as shown on your screen. It gets an input W, and then it guesses a certificate of length at most D times n to the k. And then it runs the verifier V on the pair W comma C. If V accepts, it accepts W, otherwise it rejects. This is a non-deterministic Turing machine. Now let's say the W happens to be in the language L. Then there is at least one certificate such that W comma C, one certificate C, such that W comma C is accepted by this verifier. Since this non-deterministic Turing machine is guessing from all possible certificates, therefore one of its branch will guess the right certificate and that branch will accept. On the other hand, if W is not in the language, then no matter what certificate you give to the verifier rejects. Therefore, this non-deterministic Turing machine, it is guessing a certificate and all its branches are going to reject. Thus, it accepts the language L, and it's very easy to see that this non-deterministic Turing machine also runs in time order n to the k. Therefore, this language is in NP2, the class the class of problems which run in non-deterministic polynomial time. Let's now prove this fact the other way around. Let's take a language which is in NP2 and prove that it must be also in NP1. Now let L be a language in NP2. What we want to show is that L is in NP1. So L is in NP2. That means there is a non-deterministic Turing machine that accepts this language L, and it runs in polynomial time, say D times n to the k. So we have a language for which we have a Turing machine, non-deterministic Turing machine, and this non-deterministic Turing machine accepts this language in polynomial time. What we want to do is now we want to somehow construct a verification algorithm for this language that would show that this language is also in NP2, is also in NP1, and therefore it will show that both of these definitions give us the same class NP. Well, think about it. How will we construct a verification algorithm for L? Remember, the verification algorithm cannot have any non-determinism in it. It can only be deterministic. So, suppose that you want to convince somebody that a particular string W belongs to L. How would you go about it? You don't know much about L. The only thing you know about L is that there is a non-deterministic Turing machine that accepts that language. So one way to convince somebody that X is in L is to convince them that this non-deterministic Turing machine will accept this X. However, a non-deterministic Turing machine makes choices. Its computation is a huge tree. Suppose you can also find out what branch of this tree will lead to accepting computation. Then you can convince somebody that X is in L by saying, look, X is in L because this non-deterministic Turing machine accepts X. And the reason this non-deterministic Turing machine accepts X is by following this exact branch. If you follow this exact branch, then this non-deterministic Turing machine reaches the accepting configuration, and therefore it accepts X. Now, this is actually a proof of the fact that X is in L. And we can use this idea to come up with a verification algorithm. If you look at a non-deterministic Turing machine, the non-deterministic Turing machine makes a choice at every step. Suppose there are at most p possible choices. And suppose we take a string, so for example, there's a string 1, 3, 1, 1, and so on. This string tells us that run the machine M, and from the first state make the first choice. From there on make the third choice. From there on make the first choice again and the first choice again. So if you're given this string, a string which tells us which choices the non-deterministic Turing machine will take, this string is telling us which branch of the computation tree to follow in this non-deterministic Turing machine. Once we are given this string which is telling us what choices to make, the non-determinism goes away and a deterministic Turing machine can simulate this non-deterministic Turing machine. And that's going to be our verifier. So formally our verifier is given as follows. It will take an input W and a C. So the W is the string that it wants to verify, it's an L, and C is the proof. It is going to interpret C as telling it which branch of the non-deterministic Turing machine to follow, which choices to make at every step. So what it will do, it will simulate the non-deterministic Turing machine on W by making choices which are dictated by C. So what is this verifier? What language is this verifier verifying? Well, let's think about it. Suppose W is in L, then the non-deterministic Turing machine M accepts W. This means that there is a sequence of choices that this non-deterministic Turing machine makes which leads it to an accepting configuration. Or said in another way, there's at least one branch in the computation tree which leads it to an accepting configuration. Now if that particular sequence of choices is given to this verifier will accept W. It will take W and make exactly those choices and finally realize that M is accepting W, so it will accept W, C. So it's verifying if W accepts, if M accepts W via the choices C. On the other hand, what would happen if W is not accepted by the non-deterministic Turing machine? Well, in this case, what we know is that all branches in the computation tree of M lead to a rejecting state. So no matter what set of choices or sequence of choices you give to this verifier, when it simulates M, it will always reach a reject state. So it will always reject W, C for those W's which are not in the language. Therefore, this is a verifier for the language L. So L is in NP1. So what we have shown is that if a language is accepted by a non-deterministic Turing machine in polynomial time, then it has a polynomial time verifier. On the other hand, if a language has a polynomial time verifier, then it is accepted by a non-deterministic Turing machine in polynomial time. NP1 was defined to be the set of all languages that are accepted by non-deterministic Turing machines in polynomial time, and NP2 was defined to be the set of all languages for which we have polynomial time verifiers. Thus, these two definitions are equivalent and they define one class NP. This justifies that now we can get rid of the subscript NP1 and NP2. Since both of them are equal, we can call both of these classes, which is actually one class, NP. This is very typical in mathematics. Sometimes some concepts, mathematical concepts, can be defined in more than one way. In one way and also in another way. So if that happens, what mathematicians do is they show that both these definitions give us the same concept, and this gives us an alternate way of looking at that concept of that or that structure. We're actually very lucky that non-determinism, NP, has two equivalent definitions. This means that this elusive concept can be understood in two ways. So if I ever give you a problem and say, show that this language is in NP, what you can do is you can follow the first approach, which is to design a non-deterministic polynomial time Turing machine for that language, or you can design a verification algorithm. Actually, what you should do is you should design both. That way, you would understand the problem more clearly and you will be able to relate these two concepts. Let's look at one more example and see that this language is also in NP. Let us define clique to be the set of all pairs G, K, where G is going to be an undirected graph and the graph has to have a clique of size K. So the input to this problem is a graph and a number K, and the question is, does this graph G have a clique of size K? Well, in order for us to understand this problem completely, what we have to do is first recall what a clique in a graph is. A clique S is a set of vertices which are all connected to each other. So a clique S is a bunch of vertices in a graph such that between any two pair of vertices in that set, they are connected with an edge. There is an edge between them. That's what we call a clique. Here is a picture of a clique for you. This picture shows a graph in which every vertex is connected to every other vertex, and therefore it is called a clique. Here is another graph. This graph itself is not a clique, but it contains a clique of size 4 because there are 4 vertices in it which are all connected to each other. So these 4 vertices mutually have 6 edges between them. We have bolded out the clique for you to see. So a clique in a graph is a set of vertices which are all connected to each other. The size of the clique is, of course, the number of vertices in a clique. So now the clique problem is, given a graph and a number K, you have to tell whether the graph has a clique of size K. If it does, you accept the input, otherwise you reject. So what we want to do is, we want to show that this problem called clique, or this language called clique, is in NP. Well, we can start thinking about how to prove that this language is in NP. Either we have to make a non-deterministic Turing machine which accepts this language in polynomial time, or think of a verification algorithm which can verify if a graph has a clique of size K in it. Well, let's think about it from the verification point of view. So suppose you have a graph and suppose you knew that it had a clique of size K in it. How will you convince somebody that it has a clique of size K in it? What would be the best possible proof that this graph has a clique of size K? So for concreteness, let's say you have a graph on 50,000 vertices and you know that somehow you know that this graph has a clique of size 200 in it. Well, the best or the easiest proof or easiest way to convince somebody that your graph has a clique of size 200 in it is to show them the clique of size 200. Identify the 200 vertices which are mutually connected with each other. If you identify to them the 200 vertices which are all connected to each other, each pair is connected with each other, they'll be able to verify that these vertices form a clique very easily. Thus, the clique problem has an easy verification algorithm. Let's look at this algorithm formally and in more detail. On input G, W and a set S. So S is going to be the vertices which we are claiming are the clique inside this graph. All we have to do is first check if the size of S is K, and then check if for every pair of vertices in S, if every pair of vertices A, B in the set S, A and B is indeed an edge in the graph. This is a simple verification algorithm. And this algorithm verifies whether a graph has a clique of size K or not in it. Thus, the clique problem is in NP. Well, let's think about what we have actually done today. In the last lecture, we had looked at the class P and we said P is the set of all problems which can be solved in polynomial time using deterministic Turing machines. Now we have defined the class NP, which is the set of all problems for which we have verification algorithms, polynomial time verification algorithms. One of the most intriguing questions, in fact, the most important, the central question in complexity theory and all of computer science is whether these two classes of languages are the same or not. It is very easily seen that P is a subset of NP. That is because every deterministic Turing machine is also a non-deterministic Turing machine. It simply doesn't use any non-determinism. Therefore, P is a subset of NP. Whether P is a proper subset of NP or not is the most interesting question. Is there a problem which is inside NP but not in P? Is there any single problem like that? This is the most intriguing and one of the most important problems in computer science and in logic. Unfortunately, we do not know the answer to this problem. However, we will study the classes P and NP and see why this question is so important and why it is so intriguing. Actually, this problem is so important that the Clay Mathematical Institute has announced $1 million for anyone who can resolve this question. So, the P versus NP question has a $1 million bounty on it. Well, we will look at this problem, the P versus NP question, more in detail in the next lecture. I'll see you next time. Thank you and goodbye.